So plotting motion on a position versus time graph is actually pretty straightforward, but actually gives you a whole lot of information, and we're going to be using these for a while. So let's talk about making them and what we can get from them. So the first thing you want to do always is label your graph. Let's make this one about my morning bike ride. And the y-axis is always your dependent variable, and your x-axis is always your independent variable. So in a position versus time graph, time is always going to be your independent variable because time just moves on and on and on, and doesn't really care about your position. The time will just keep going. That is the independent variable. Position is your dependent. So position will go here, and we'll give it a label and a unit. And based on this unit, we'll give time the appropriate unit as well. Whatever you're measuring the time in, that's what you'll give it. So distance from home. This is strange because we just talked about the difference between distance and displacement, and this says distance, but you have to realize this says distance from home. So we're considering away from home is the positive and towards home is the negative. So that's actually a displacement because I can go away from home and then back and have gone 0 distance from home, even though I've traveled a longer distance than that. So just be aware that this is actually a displacement and not a distance. Distances can't be negative. If I walked 10 yards away and walked 10 yards back, then my distance was 20. But my displacement is 0. So I'm in the same spot. Okay, well, if I'm starting from home, then my position, distance from home, is 0. And if I'm starting, then my time is 0 as well. So here I am at 0, 0. No time has passed and I have not left yet. So once I start going, my time will start and my distance will start rising. So let's say in 2 hours, I'm about 14 miles from home. Let's say 2 hours, 14 miles from home. This is a weekend morning, clearly. I obviously don't have anything to do. Let's say 14 miles away and 2 miles in, I actually arrived at a park. Let's say I met a friend there. And they ended up inviting me to stay for lunch and a picnic, and we hung out for a while, had a jolly time. I haven't been moving any further from home, but I stayed with my friend at the park for 3 hours. So from 2 hours to 3 hours, from 2 hours to 5 hours, that's 3 hours at the park, I didn't move at all. I'm still 14 miles from home. So here's my dot. Well, by then I'm pretty tired, so I'm trying to ride my bike home. Luckily, it is downhill on the way home, so I can go a little bit faster, and I make it home in about 1.5 hours instead of 2. So let's say in 1.5 hours I'll be at 6.5, and I'll be home. So my distance from home is now 0. So these are my 4 points. I started at home at time 0. After 2 hours, I'm at 14 miles from home. And then I stayed there for 3 hours. I'm still at 14 miles from home. And then I went back. Let's connect these with a line. So you can see as I'm moving away, it's going upward. I'm gaining distance from home. And then this flat line's a little bit here, means I'm not moving at all. My distance is not changing. And then on my way back, I'm losing distance from home. So of course this is negative because this is displacement and not actually distance. Let's read another graph. We're going to venture into the exciting world of turtle racing and look at this turtle position versus time graph. So the position, it has a title. The position is in centimeters and the time is in seconds. So we have different measurements here, and I can tell that he went a little under 50 centimeters in 20 seconds, a little under 100 centimeters in 40 seconds, somewhere right in the middle of 100 and 150 in 60 seconds, and so on. That's pretty straightforward. Let's compare him to an actual turtle race. And we'll look at this graph. Here's two turtles in a race. One of them is clearly doing much better than the other. Well, which one? I can tell which one because I can see the position versus their time. So in these 200 seconds, this turtle has gone much farther, has gone 400 centimeters. This turtle has only gone 200 centimeters. And this one that's above the other in position is clearly going farther and faster. How can we tell it's faster? I can tell it's farther because it's above on the position. So it's definitely farther. How can I tell it's faster? I can tell that this turtle is going faster because the line is steeper. It's more steep than this one. This one's laying more flat. Well, what if I wanted to prove it? What if I wanted to actually say, how fast are these turtles moving? Well, that's interesting. We have all the information that we need. How do we find speed or velocity? It's just the distance over the time. In this case, we have the distance and we have the time. So all we need is a change in. So velocity is actually the change in displacement over the change in time. These are the Greek symbols delta. They're little triangles. They mean change in. Maybe you've seen them before. So we need to actually pick 2 points. 0, 0 is an easy one. And I know this one right here. That is 200, 400. Hopefully this will look familiar to you from math class. We've got 0, 0 down here. And we have 200, 200 right here. So for the red turtle, what was my change in displacement? Well, I started at 0 and I ended at 400. So that is 400. What is my change in time? I started at 0 and I went to 200, so that is 200. 400 divided by 200 is 2 centimeters every second. Centimeters every second. What about the green guy? The green guy went from 0 to 200 in his position. The green guy went from 0 to 200 in his time, and that is 1 centimeter per second. So we have a position versus time graph, but we also have the information that tells us the speed, the velocity in this case, because we have position, we have a displacement and not a distance. Now the great thing about working with units, and something that I'm going to continue to bring up since we were doing conversions, is that the units actually tell you if you're right. This displacement is in centimeters. This time is in seconds. So you know your final answer will be centimeters per second. And that is a speed. That's what you want, 2 centimeters per second. Here, the distance, centimeters. Time, seconds. We know this is right, centimeters per second. If you were to say, I can't remember if speed is time over distance or distance over time. Just think of a speed. What's a speed? Miles per hour. Miles per hour. Okay, that is distance, and this is time. The units will always tell you the answer. So hopefully this looks familiar to you from math class, because when I say velocity is change in displacement over change in time, displacement is on the y-axis, so that's change in your y variable, over time, which is your x-axis, so that's change in my x variable. So this is change in y over change in x, which is just finding the slope. The slope of the line will be your speed. The change in y is the difference in the two y values. The change in x is the difference in the two x values. Or you might have also heard rise over run. How much does our position change? How much do we go up and down? How much does our time change? How much do we go left and right? Rise over run. So in this example, this person is moving from 0, 0 to 360. So we can say we rose 60 from 0 to 60, so 60 minus 0. And we went from 0 to 3, so we ran 3. So rise over run is going to be 60 over 3, which is 20 meters per second. So the mere fact that we have every position at any time gives us the information that we need to find the velocity, which is just the slope. So change in displacement over change in time. Where am I compared to where I was, and how long did it take? That's all the information I need to find the velocity.